Hello, and welcome to Late Physics. If you enjoy slow, thoughtful explorations of the universe, don't forget to like the video and subscribe to the channel. And before we begin, I'd love to know, where are you watching or listening from tonight? Maybe you're in a quiet room, a dimly lit city, or somewhere far from artificial light, under a sky filled with stars. Wherever you are, it's worth remembering. The same strange rules we're about to explore are quietly shaping everything around you and everything within you. Because beneath the calm, familiar surface of everyday life, something deeply unusual is taking place. The world we experience feels stable, solid, predictable. Objects sit where we leave them. Causes lead to effects. Time moves forward in a steady, reassuring way. It all feels so natural that we rarely question it. But at the smallest scales of reality, this sense of order begins to dissolve. Particles do not settle into single positions. Instead, they exist in a haze of possibilities. Events do not unfold with certainty, but with probability. And in some cases, distant objects appear to share a connection that seems to ignore the very idea of space between them. Even for the scientists who study it, the quantum world does not feel like an extension of common sense. It feels like stepping into a reality that plays by entirely different rules. And yet, those rules are not abstract. They are the foundation of everything. Every atom in your body, every beam of light, every piece of technology you rely on. All of it emerges from this quiet, hidden layer of the universe. A layer that behaves in ways that seem, at first, almost impossible to grasp. So why does it feel so mysterious? Is it because the theory is incomplete? Because we lack the right tools? Or is it something deeper, something about the limits of human intuition itself? Tonight, we'll take our time exploring these questions. We'll move gently from the familiar world of classical physics into the strange and subtle landscape of quantum mechanics. Along the way, we'll encounter ideas like superposition, uncertainty, and entanglement, not as abstract concepts, but as windows into a reality that is far richer and far less intuitive than it first appears. And as we go, we'll see that the mystery of the quantum world is not just a puzzle to be solved. It may be a reflection of something fundamental, a reminder that the universe at its deepest level is not obligated to match the way we expect it to be. So, settle in, wherever you are in the world tonight, and let's begin a slow journey into one of the most fascinating and quietly unsettling discoveries in all of science. The realization that reality itself may be far stranger than it feels. If you pause for a moment and look around you, everything seems reassuringly stable. The surface beneath you feels solid. Objects remain where they are placed. Light travels in straight lines, and time appears to move forward with quiet consistency. The world at this scale behaves in ways that feel not only predictable, but deeply familiar. It is a kind of reliability that most of us rarely question. And yet, hidden beneath this calm and orderly surface, there is a layer of reality that behaves in ways that seem almost deliberately unfamiliar. Quantum physics is often introduced as a branch of science that studies very small things, electrons, photons, atoms. But that description, while technically accurate, misses something far more important. It is not simply that quantum physics looks at smaller objects. It is that, at those scales, the very rules that govern reality begin to change in subtle but profound ways. This is where the sense of mystery begins. Because the difficulty is not just that the quantum world is complicated, it is that it does not behave in ways that align with the expectations we have built from everyday experience. Our intuition has been shaped by objects we can see, touch, and move, things that have definite positions, definite speeds, and clear boundaries. Quantum systems do not always offer those certainties. Instead, they introduce a different kind of structure, one that is precise, mathematically consistent, and extraordinarily well tested, but not immediately intuitive. This difference can feel like a kind of quiet shock, not dramatic or chaotic, but deeply disorienting in a gentle way. The realization that the foundation of reality may not resemble the surface we are used to. To understand why this feels so unsettling, it helps to consider how scientific understanding usually evolves. For long periods of time, science progresses by refining existing ideas. Measurements become more accurate, models become more detailed, predictions become more precise. The overall framework remains intact, even as it improves. But occasionally, something different happens. A new discovery does not simply refine the old framework, it replaces it. The historian of science Thomas Kuhn described this process as a paradigm shift, a moment when the underlying assumptions of a field are no longer sufficient, and a new way of thinking must take their place. These shifts are not always comfortable. They require scientists to let go of ideas that once seemed certain and to accept that reality may be structured in ways that were previously unimaginable. Quantum physics represents one of the most significant paradigm shifts in the history of science. Before its development in the early 20th century, the dominant view of the universe was shaped by classical physics. The work of Isaac Newton and those who followed had created a picture of reality that was, in many ways, beautifully simple. Objects moved according to clear laws. If you knew the position and velocity of something, you could, in principle, predict its future behavior with complete certainty. This idea was later expressed in a particularly vivid way by Pierre-Simon Laplace. He imagined a hypothetical intelligence, now often called Laplace's demon, that could know the position and motion of every particle in the universe. With that knowledge, it could calculate the entire future and the entire past with perfect accuracy. It is a powerful image. A universe that unfolds like a perfectly designed clock, every motion determined, every outcome predictable. Quantum physics quietly removes that certainty. Not because scientists lack the tools to measure precisely enough, but because the underlying structure of reality does not allow for that kind of complete prediction. At very small scales, systems are not described by definite values in the same way. Instead, they are described by ranges of possibilities, each with its own likelihood. This is not a temporary limitation. It is built into the theory itself. And yet, despite how strange this sounds, quantum mechanics is not a vague or uncertain science. In fact, it is one of the most accurate and successful theories ever developed. Its predictions have been confirmed to extraordinary precision. Technologies based on quantum principles, from semiconductors to lasers, function reliably every day. So the mystery does not come from a lack of understanding in the usual sense. It comes from the fact that the structure being described does not match the patterns our minds expect. In classical physics, it is natural to imagine that objects have properties whether or not we observe them. A ball has a position, even if no one is looking at it. A planet follows a path through space, regardless of whether it is being measured. These assumptions feel so obvious that they hardly seem like assumptions at all. Quantum physics gently challenges this way of thinking. At the quantum level, the properties of a system are often not defined in the same way until an interaction takes place. Before that interaction, the system is described by a mathematical object known as a wave function. This wave function does not assign a single definite outcome. Instead, it encodes a set of possible outcomes, each with a specific probability. When a measurement occurs, one of those possibilities is realized. This idea can feel subtle at first, but its implications are profound. It suggests that the world, at its most fundamental level, is not built from fixed, sharply defined properties in the way we might expect. Instead, it is structured around possibilities that become actual only under certain conditions. For many scientists, this was not an easy idea to accept. Even Albert Einstein, who played a crucial role in the early development of quantum theory, expressed discomfort with its probabilistic nature. He famously remarked that he could not believe that nature played dice with the universe. It was not a rejection of the theory's accuracy, but a reflection of how deeply it challenged existing intuitions about how reality should behave. Over time, however, the evidence continued to accumulate. Experiments became more refined. Predictions continued to match observations with remarkable precision. The mathematical framework held firm, and so, physicists gradually came to accept that the quantum world is not a flawed version of classical reality. It is a different kind of reality altogether. This distinction is important because it shifts the source of the mystery. The difficulty is not that the theory is incomplete or poorly tested. It is that the conceptual framework required to understand it does not align with the mental models we have developed through everyday experience. In other words, the challenge is not just scientific, it is cognitive. Our brains are remarkably good at navigating the world we evolved in. They are tuned to recognize patterns, anticipate motion, and make quick judgments about physical interactions. But those abilities are shaped by a world of medium-sized objects moving at relatively low speeds. They are not designed to intuitively grasp the behavior of electrons or photons. So when we encounter quantum concepts, There is often a gap between what the mathematics tells us and what our intuition expects. The mathematics is precise and reliable. The intuition lags behind. This gap is where the feeling of mystery lives. It is not a sign that something is wrong. It is a sign that we are exploring a layer of reality that lies beyond the familiar boundaries of everyday experience. And perhaps, in a quiet way, that is part of what makes the quantum world so compelling. It reminds us that the universe is not limited to what feels obvious, that beneath the calm surface of ordinary life, there exists a deeper structure, one that operates according to principles that are subtle, elegant, and not always easy to picture. As we continue, we will move gradually into some of those principles, not to resolve the mystery completely, but to understand where it comes from and why it persists. Because sometimes, the most interesting discoveries are not the ones that make the world feel simpler, but the ones that gently reveal just how much more there is to understand. For a long time, the universe appeared to follow a quiet and reassuring promise. If you knew enough about the present, you could predict the future. This idea did not emerge casually. It was built carefully, piece by piece, through the work of scientists who observed the world with remarkable precision. At the centre of this effort was Isaac Newton, whose laws of motion and universal gravitation described how objects move and interact. Newton's framework is elegant in its simplicity. It tells us that forces cause acceleration, that motion follows clear mathematical relationships, and that these relationships remain consistent across time. A falling apple and the orbit of the moon are governed by the same principles. With the right information, their behaviour can be calculated. One of the most important aspects of this picture is determinism. Determinism is the idea that the state of a system at one moment completely determines its state at the next. If you know the position and velocity of an object and the forces acting on it, then its future path is fixed. There is no ambiguity, no randomness, only unfolding certainty. This way of thinking reached its most striking expression in the early 19th century through the work of Pierre-Simon Laplace. Laplace imagined a hypothetical intelligence, often referred to as Laplace's demon. This entity would possess complete knowledge of the positions and velocities of all particles in the universe, along with the laws that govern their motion. With that information, it could calculate the entire future and the entire past with perfect accuracy. In Laplace's vision, the universe is like an immense and intricate clock. Every gear, every movement, every interaction is precisely determined. Nothing is left to chance. Even events that appear random, like the roll of a die or the flicker of a flame, are, in principle, fully predictable if one has enough information. It is a powerful and deeply appealing idea. It suggests that uncertainty is not a feature of the universe itself, but a limitation of human knowledge. If we cannot predict something, it is simply because we do not yet have all the necessary details. For a time, this view seemed not only reasonable, but almost unavoidable. The success of classical physics was extraordinary. Newton's laws could predict the motion of planets with remarkable accuracy. The return of comets, the tides of the oceans, the trajectories of projectiles, all could be calculated and confirmed. The universe appeared orderly, lawful, and comprehensible. However, as measurements became more precise and scientific inquiry pushed into new domains, subtle cracks began to appear in this picture. One of the earliest hints that predictability might not be as absolute as it seemed came from the work of Henri Poincaré in the late 19th century. Poincaré was studying the motion of three gravitationally interacting bodies, a problem known as the three-body problem. Unlike simpler systems, this problem does not have a general solution that can be expressed in a neat closed form. Instead, Poincaré discovered that even tiny differences in initial conditions could lead to dramatically different outcomes over time. This sensitivity to initial conditions means that in practice, long-term prediction becomes extremely difficult. Even the smallest uncertainty in measurement can grow and amplify, eventually making accurate forecasts impossible. This idea would later become a central feature of what we now call chaos theory. At first glance, this might seem like a challenge to determinism. If systems are so sensitive that we cannot predict them, does that mean they are not deterministic? The answer, interestingly, is no. Chaotic systems are still governed by deterministic laws. Their future is still fixed by their initial conditions. The difficulty lies not in the nature of the laws, but in our ability to measure and calculate with perfect precision. In other words, chaos introduces practical unpredictability, but not fundamental randomness. The universe, in this view, remains a clock. It is simply a clock that is so complex and so sensitive that we cannot follow every gear as it turns. Quantum physics introduces a different kind of break, not a limitation of measurement, but a limitation of the structure itself. When scientists began to investigate phenomena at very small scales, such as the behavior of electrons and photons, they found that the classical framework could no longer provide accurate predictions. The equations that worked so well for planets and projectiles began to fail. In their place, a new mathematical framework emerged, one that did not assign definite outcomes in the same way, but instead described probabilities. This shift is subtle, but profound. In classical physics, if you know the initial conditions, the outcome is determined. In quantum mechanics, even with complete knowledge of the system, the outcome can only be described in terms of likelihoods. This is not because something is missing from the theory, it's because the theory itself is built around probability. For example, when an electron passes through an experimental setup such as a double-slit apparatus, it does not follow a single, well-defined path in the classical sense. Instead, its behavior is described by a distribution of possible outcomes. When a measurement is made, one specific result is observed, but the theory does not predict which one will occur with certainty. It only provides the probabilities. This represents a fundamental departure from the deterministic universe imagined by Laplace. The idea of Laplace's demon no longer holds in the same way. Even with complete information about a quantum system, there is no way to predict a single outcome with absolute certainty. The best one can do is calculate the probability of each possible result. This is sometimes described as indeterminacy. It's important to distinguish this from ignorance. In classical systems, uncertainty often arises because we do not know all the details. In quantum systems, uncertainty is built into the description itself. It is not something that can be removed by better measurement or more precise instruments. This difference is what makes the transition from classical to quantum thinking so significant. Chaos theory showed that even deterministic systems can behave unpredictably in practice. Quantum mechanics goes further, suggesting that unpredictability is woven into the fabric of reality. This idea was not immediately accepted. Many physicists, including Albert Einstein, found it difficult to reconcile with their understanding of the universe. Einstein's discomfort was not with the accuracy of quantum mechanics, which he helped to develop, but with its implications. The notion that events could occur without a definite cause, or at least without a predictable outcome, seemed incomplete. Yet, over time, experiments continued to confirm the predictions of quantum theory, with extraordinary precision. The probabilistic framework was not a temporary placeholder. It was a reliable and consistent description of nature at small scales. And so, the picture of the universe began to change. No longer a perfectly predictable clock, but something more subtle. A system where certainty gives way to probability, where outcomes are not fixed until they occur, and where the future is not entirely determined by the past. This does not mean that the universe is chaotic in a careless or arbitrary sense. Quantum mechanics is governed by precise mathematical rules. The probabilities it predicts are exact and testable. The behavior of systems follows well-defined patterns, even if individual outcomes cannot be predicted with certainty. In a quiet way, this makes the universe both more structured and more mysterious. More structured, because the underlying mathematics is extraordinarily precise. More mysterious, because the nature of prediction itself has changed. What once seemed like a simple question, what will happen next, now has a different kind of answer. Not a single outcome, but a range of possibilities. And perhaps, just as gently as it arrived, the idea of a fully predictable universe begins to fade, replaced by something that is no less lawful, but far less certain. At first glance, the universe appears smooth. Light seems to flow continuously. Energy appears to change gradually. Motion unfolds without obvious gaps or steps. If you dim a lamp, the brightness fades steadily. If you heat an object, its temperature rises in a seemingly unbroken way. For a long time, physicists assumed this smoothness extended all the way down to the smallest scales. But at the beginning of the 20th century, that assumption began to unravel in a very specific and unexpected place. The problem was known as blackbody radiation. A blackbody is an idealized object that absorbs all incoming light and then re-emits energy depending on its temperature. When physicists tried to calculate how much energy such an object should emit at different frequencies, classical physics produced a result that was not just slightly incorrect, but dramatically so. According to classical equations, the energy emitted at high frequencies should increase without limit. This prediction became known as the ultraviolet catastrophe. It suggested that even a warm object, like a piece of metal, should emit an enormous amount of high-frequency radiation. Clearly, this does not happen. In reality, the energy emitted by a black body peaks at a certain frequency and then falls off. The observed behavior is smooth and well-behaved. The classical prediction is not. This mismatch presented a serious challenge. In 1900, Max Planck proposed a solution that was, at the time, almost reluctant. He suggested that energy is not exchanged continuously, but in discrete amounts. Instead of being able to take on any value, energy could only be emitted or absorbed in specific packets, which he called quanta. To describe this, Planck introduced a relationship between energy and frequency. In clear-spoken terms, it can be expressed as energy equals Planck's constant multiplied by frequency. Planck's constant is a very small number, approximately 6.6 times 10 to the minus 34 joule-seconds. Because it is so small, the discrete nature of energy is not noticeable at everyday scales. The steps are far too tiny to detect in ordinary situations. But at very small scales, those steps become significant. With this single assumption, Planck was able to produce a formula that matched the observed spectrum of blackbody radiation with remarkable accuracy. The ultraviolet catastrophe disappeared, replaced by a curve that aligned perfectly with experimental data. At the time, Planck viewed this idea as a mathematical trick, a useful way to make the equations work, rather than a statement about the true nature of reality. But the implications were far deeper than that. If energy is quantized, then the universe is not entirely smooth. There are limits to how energy can be exchanged. There are smallest units beyond which division is no longer possible. This idea did not remain isolated. A few years later, in 1905, Albert Einstein used the concept of quantization to explain the photoelectric effect. He proposed that light itself could behave as if it were made of discrete packets, later called photons. This was not just energy being quantized, but light itself taking on a particular character. Gradually, the idea of quantization began to spread. Electrons in atoms were found to occupy discrete energy levels. They could not exist at arbitrary energies, but only at specific allowed values. When an electron transitions between these levels, it absorbs or emits a photon with an energy that exactly matches the difference between them. This is why atoms produce distinct spectral lines, rather than continuous bands of color. Each line corresponds to a specific jump between quantized energy levels. The more physicists explored these systems, the clearer it became that quantization was not a temporary fix, or a convenient approximation. It appeared to be a fundamental feature of nature. This raises an interesting question. If energy is quantized, what else might be? Is it only certain properties that come in discrete units, or is discreteness woven more deeply into the fabric of reality? Some physicists have taken this idea further, suggesting that quantization may extend beyond energy and matter to include space and time themselves. One of the most influential voices in this direction was John Archibald Wheeler. Wheeler proposed a striking phrase, "it from bit." The idea behind this phrase is that physical reality, the it, may ultimately arise from informational building blocks, the bits. In this view, the universe is not just made of particles or fields, but of information. The act of measurement, the distinction between one outcome and another, becomes central. Rather than imagining reality as a continuous substance, Wheeler encouraged thinking of it as something that emerges from discrete acts of information. This perspective does not replace quantum mechanics, but it offers a different way of interpreting its structure. It suggests that the discreteness observed in energy levels and quantum states may reflect a deeper informational structure beneath physical phenomena. Another approach to this idea can be found in the work of Carlo Rovelli and others studying loop quantum gravity. Loop quantum gravity is an attempt to unify quantum mechanics with general relativity, Einstein's theory of gravity. One of its key proposals is that space-time itself is not continuous, but quantized. In this framework, space is made up of tiny, discrete units, often described as loops or networks. These units are incredibly small, on the order of the Planck length, which is about 1.6 times 10 to the minus 35 meters. To give a sense of scale, if you were to magnify a single atom to the size of a galaxy, the Planck length would still be far smaller than anything you could observe within that galaxy. At such scales, the familiar notion of smooth space breaks down. Instead of a continuous backdrop, space becomes something more like a finely woven structure, composed of individual elements. Time, too, may have a smallest meaningful interval, known as the Planck time, roughly 5.4 times 10 to the minus 44 seconds. These ideas are still being explored and tested. Loop quantum gravity is one of several competing approaches to understanding quantum gravity, and it remains an active area of research. But what makes it particularly interesting in this context is how it extends the concept of quantization. From energy, to light, to matter, and potentially to space-time itself, the pattern is consistent. Where classical physics sees smoothness, quantum theory often reveals discreteness. This shift changes how we think about continuity. In everyday experience, continuity feels natural. We expect things to vary smoothly, without jumps or gaps. But if the underlying structure of reality is discrete, then continuity may be an emergent property, something that appears at larger scales when many small units are combined. This is similar to how a digital image can appear smooth from a distance, even though it is made up of individual pixels. The resolution is high enough that the discreteness becomes invisible. In the same way, the world we experience may appear continuous because the underlying units are so small and so numerous that their individual nature is hidden. Seen from this perspective, quantization is not just a technical detail. It is a clue, a hint that the universe may be built from fundamental units, whether of energy, information, or space-time itself. It suggests that the smoothness we perceive is not the most basic layer of reality, but a large-scale approximation. And perhaps this is part of what makes the quantum world feel so unusual. It asks us to let go of the assumption that everything can be divided endlessly, that change is always gradual, that the fabric of reality is seamless. Instead, it offers a different picture, one where there are limits, where there are smallest units, where the structure of the universe is not infinitely divisible but composed of discrete building blocks, not immediately visible, not easily imagined, but quietly present beneath everything we observe. And in that quiet discreteness, there is the suggestion of something deeper, not just a different way of calculating outcomes, but a different way of understanding what reality is made of. When most of us imagine the building blocks of reality, we tend to picture small, solid things, tiny particles like miniature billiard balls, moving through space, colliding, bouncing, and interacting in predictable ways. It is a natural extension of how we experience the world around us. Larger objects are made of smaller pieces, and those pieces are made of even smaller ones, continuing down until we reach what feels like the most basic layer. For a time, this picture worked remarkably well. Atoms were understood as small, discrete units. Inside them, electrons orbited a central nucleus, itself made of protons and neutrons. And inside those, even smaller components were discovered. Each step seemed to bring us closer to the idea of fundamental particles, the smallest possible pieces of matter. But as physics developed further, especially through the 20th century, this picture began to change in a subtle but important way. The idea of particles as tiny, solid objects started to dissolve. In its place, a different framework emerged, one that is now known as quantum field theory. Quantum field theory is not just an extension of quantum mechanics. It is a deeper way of describing what exists at the most fundamental level. Instead of beginning with particles, it begins with fields. A field is something that exists throughout space. It assigns a value to every point in space and time. One familiar example is the gravitational field, which describes how mass influences the motion of objects. Another is the electromagnetic field, which governs how charged particles interact with light. What quantum field theory proposes is that these fields are not just convenient descriptions, they are the fundamental reality. According to this view, the universe is filled with a collection of underlying fields. There is an electron field, a photon field, a quark field, and many others. Each type of particle corresponds to its own field, extending everywhere, even in what we might casually think of as empty space. A particle, in this framework, is not a small object sitting inside the field. It is a localized excitation of the field itself. This idea can be understood through a simple analogy. Imagine a calm surface of water, stretching out in all directions. The water itself is the field. If you disturb the surface, perhaps by dropping a small pebble, ripples form. These ripples are not separate from the water. They are patterns within it, temporary movements that travel across the surface. In a similar way, what we call a particle is like a ripple in a quantum field. It is not a standalone object, but a disturbance, a localized concentration of energy within a field that exists everywhere. This shift in perspective changes how we think about the nature of matter. Instead of solid building blocks, we have dynamic processes. Instead of fixed objects, we have patterns that arise and dissolve within underlying fields. The electron you might imagine as a tiny point is, in this view, an excitation of the electron field. A photon is an excitation of the electromagnetic field. These excitations can be created, interact, and disappear, but the fields themselves remain. Steven Weinberg, one of the key contributors to modern quantum field theory, emphasized this idea in his work on the Standard Model of particle physics. The Standard Model describes the fundamental particles and their interactions with remarkable precision, and it is built entirely within the framework of quantum fields. According to this model, the properties of particles, such as mass and charge, arise from how these fields behave and interact. For example, the Higgs field plays a role in giving mass to certain particles through a process known as spontaneous symmetry breaking. This means that even something as seemingly intrinsic as mass is not a fixed property of a tiny object, but a result of interactions within a field. It is a subtle but profound shift. What we perceive as objects are, at a deeper level, events. Temporary, structured patterns in a continuous background of fields. This perspective can feel unfamiliar, even slightly unsettling, because it removes the sense of solidity that we're used to. The idea that things are not truly things, but processes, requires a different way of thinking. Philosophers of science have explored this shift as well. Nancy Cartwright, for example, has written about how scientific theories often provide models that work in specific contexts, rather than offering a single, unified picture of reality. From her perspective, the entities described by physics are not always straightforward reflections of what exists, but tools that help us understand and predict phenomena. In the case of quantum field theory, the concept of a particle is itself somewhat flexible. In different contexts, what counts as a particle can change. In some situations, particles can be created or destroyed. In others, what one observer describes as empty space, another might describe as filled with particles depending on their state of motion. This suggests that the notion of a particle as a fixed, independent object is not as fundamental as it once seemed. Instead, the underlying fields take on that role. Another interesting consequence of this framework is how it reshapes our understanding of empty space. In classical physics, empty space is simply the absence of matter, a quiet backdrop against which events unfold. In quantum field theory, empty space is anything but empty. Even in a vacuum, the lowest energy state of a field, there are fluctuations. Temporary excitations can appear and disappear, a phenomenon often referred to as vacuum fluctuations. These effects have measurable consequences, such as the Casimir effect, where two uncharged metal plates placed very close together experience a small force due to changes in the vacuum energy between them. So the idea of nothing becomes more complex. What appears to be empty is actually a dynamic environment, filled with potential activity at extremely small scales. All of this contributes to a gradual shift in how we think about reality. The solid, stable objects of everyday experience are still useful and meaningful at larger scales. A table is still a table. A chair remains a chair. But at the deepest level currently understood, those objects are not fundamental. They are composed of patterns within fields, patterns that persist long enough and interact in consistent ways, giving rise to the stability we observe. This does not make the world less real. If anything, it reveals a deeper layer of structure beneath what we see. But it does challenge the idea that reality is built from small, solid pieces. Instead, it suggests that what exists are fields, continuously present, and the excitations within them, which we perceive as particles. A universe not of objects, but of processes. Not of static building blocks, but of ongoing activity. And perhaps this is another reason the quantum world feels so mysterious. because it asks us to replace a picture that feels simple and familiar with one that is more abstract, more dynamic, and less tied to everyday experience. It is not that the world becomes chaotic or unpredictable in a careless sense. It is that the underlying structure is different from what intuition might suggest, less like a collection of tiny solid things and more like a vast interconnected system of fields, gently vibrating, interacting, and giving rise to everything we observe. There is a particular idea in quantum physics that seems to sit at the very center of its strangeness. It is called superposition. At first, it can sound like a technical detail, something abstract and mathematical. But when you take a moment to understand what it is actually saying, it begins to reshape how we think about possibility itself. In classical physics, a system is always in one definite state. A ball is either here or there. A switch is either on or off. A planet follows a single path through space. Even if we are uncertain about the details, we assume that the system itself has a precise state at every moment. The uncertainty lies in our knowledge, not in the system. Superposition introduces a different picture. In quantum mechanics, a system can exist in a combination of multiple possible states at the same time, not in the sense that we simply do not know which state it is in, but in the sense that all of those possibilities are part of its description. For example, consider an electron that can have one of two spin states, often described as spin up or spin down. In classical thinking, the electron must be in one of these states, even if we have not measured it yet. In quantum mechanics, the electron can exist in a superposition of both spin up and spin down simultaneously. This does not mean that it is rapidly switching between the two, or that it is partly one and partly the other in a simple mixture. It means that the system is described by a single quantum state that includes both possibilities at once. Only when a measurement is made does one specific outcome appear. Before that moment, the system is not in one definite state in the classical sense. This idea is often described mathematically using the wave function, which encodes the probabilities of different outcomes. But the key point is not just the mathematics, it is what the mathematics is telling us about the nature of reality. Superposition suggests that, at a fundamental level, reality is not always defined in terms of single, definite properties. Instead, it may be structured around a range of possibilities that coexist until an interaction brings about a specific result. This raises an important question. What exactly is the status of those possibilities? Are they real in the same way that a definite outcome is real, or are they simply a reflection of our incomplete knowledge? This question has been at the heart of quantum theory for more than a century, and it has led to a variety of interpretations. One approach is to treat the wave function and the superpositions it describes as representing objective features of reality. In this view, the multiple possibilities are genuinely present in some form, even if they are not directly observable in the usual sense. Another approach is to interpret the wave function as a tool for managing information rather than a direct description of physical reality. This is where the work of Christopher Fuchs and the interpretation known as quantum Bayesianism or cubism becomes relevant. Cubism takes a distinctly different perspective. According to this interpretation, the wave function does not represent an objective state of the system. Instead, it represents an agent's personal expectations about the outcomes of measurements. In other words, it encodes beliefs about probabilities rather than physical properties. From this point of view, superposition is not a statement about multiple realities existing at once. It is a statement about uncertainty and expectation. When a measurement is made, the outcome is not the revelation of a pre-existing property, but an event that updates the observer's knowledge. The probabilities change because the information available has changed. This approach shifts the focus away from the system itself and toward the relationship between the observer and the system. It suggests that some of the mystery in quantum mechanics may arise from how we interpret the role of information, rather than from the structure of reality alone. A different but related perspective can be found in relational quantum mechanics, developed by Carlo Rovelli. Relational quantum mechanics proposes that the properties of a system are not absolute, but relative to other systems. In this view, there is no single, universal description of a system's state. Instead, different observers, or more precisely different physical systems, may describe the same system in different ways, depending on their interactions with it. In this framework, superposition does not describe a system in isolation. It describes how a system appears relative to another system that has not yet interacted with it, in a way that produces a definite outcome. Once an interaction occurs, the system takes on a definite state relative to that observer, but it may still be in a superposition relative to another observer who has not yet interacted with it. This idea can feel subtle, but it offers a way of understanding superposition without requiring a single, absolute collapse of possibilities. Instead, reality becomes a network of relationships, where properties are defined through interactions rather than existing independently. Across these different interpretations, one thing remains consistent. Superposition challenges the idea that systems must always have definite properties, independent of observation or interaction. It introduces a layer of possibility that is not simply a placeholder for ignorance, but an essential part of the theory. To see how unusual this is, it can be helpful to consider how probability is used in classical contexts. If you flip a coin, you might say there is a 50% chance of heads and a 50% chance of tails. But this probability reflects a lack of knowledge about the exact conditions of the flip. In principle, if you knew the precise forces, angles, and air resistance involved, you could predict the outcome with certainty. In quantum mechanics, the probabilities are different. Even with complete knowledge of the system, the outcome of a measurement is not determined in advance. The probabilities are fundamental, not a reflection of hidden details. This distinction is what makes superposition so central to the mystery of the quantum world. It is not just that we cannot predict the outcome, it is that the system itself does not settle into a single outcome until a measurement occurs. This idea has been tested in many experiments, including variations of the double-slit experiment, where particles such as electrons produce interference patterns that can only be explained if they behave as if they pass through multiple paths simultaneously. When detectors are placed to determine which path the electron takes, the interference pattern disappears and the behavior changes. This suggests that the superposition of paths is not just a mathematical convenience, but something that has observable consequences. And yet, despite this experimental support, the question of what superposition means remains open. Is it a reflection of multiple realities existing in parallel, as suggested by some interpretations? Is it a statement about information and belief, as in Cubism? Or is it a relational property, dependent on interactions between systems? Each of these views captures part of the picture, but none has fully resolved the underlying question. And perhaps that is part of what makes superposition so intriguing. It sits at the boundary between mathematics and meaning. The equations are clear. The predictions are accurate, the experiments confirm the results. But the interpretation, the story we tell ourselves about what is really happening, remains flexible. In a quiet way, superposition invites us to reconsider what we mean by possibility, not as something that exists only in our minds, but as something that may be woven into the structure of reality itself. A range of potential outcomes, present in a subtle and interconnected way, waiting for the moment when one becomes actual. And in that gentle tension between what could be and what is observed, the sense of mystery continues to grow. Not because the theory fails, but because it reveals a world that is richer and less definite than we might have expected. There is a quiet moment in every quantum experiment that seems almost too simple to notice. A measurement is made, a detector registers a signal, a screen shows a dot, a value is recorded. Something that was previously described as a range of possibilities becomes a single, definite outcome. And yet, within that seemingly ordinary moment, there is one of the deepest and most persistent questions in all of physics. What exactly has happened? In the mathematical framework of quantum mechanics, a system evolves smoothly over time according to a rule known as the Schrödinger equation. This evolution is continuous and deterministic. The wave function, which encodes all the possible outcomes, changes in a precise and predictable way. In clear-spoken form, the central idea is often expressed as the rate of change of the wave function is proportional to the energy of the system multiplied by the wave function itself. This equation works extraordinarily well. It allows physicists to calculate how quantum systems evolve, how probabilities shift, and how interference patterns emerge. But there is a subtle gap. The Schrödinger equation describes how possibilities evolve. It does not explain how one specific outcome is selected when a measurement occurs. Before a measurement, the system is described by a superposition of possibilities. After a measurement, only one result is observed. This transition, from many possibilities to one actual outcome, is what is often called the measurement problem. It is important to approach this carefully. The measurement problem is not a failure of the theory in the usual sense. Quantum mechanics makes extremely accurate predictions about the probabilities of different outcomes. Experiments confirm these predictions again and again, often to many decimal places of precision. The question is not whether the theory works. The question is what the theory means. What is the nature of this transition from possibility to actuality? One way to begin exploring this is to reconsider what we mean by a measurement. In everyday language, a measurement often implies a conscious observer, someone looking at an instrument, reading a value, and recording it. This can lead to the impression that human awareness plays a special role in determining outcomes. However, in physics, measurement is understood more broadly. A measurement is any interaction between systems that produces a definite, stable outcome. For example, when a photon strikes a detector, it transfers energy and triggers a measurable signal. No human needs to be present at that moment. The interaction itself is sufficient to produce a result that can later be observed. This shift in perspective helps remove some of the confusion. Measurement is not about observation in the everyday sense. It is about interaction, about one system influencing another in a way that creates a lasting record. Even with this clarification, the deeper question remains. How does this interaction lead to a single outcome, rather than preserving the superposition? One of the most important developments in addressing this question is the theory of decoherence, developed in large part by Wojciech Zurek and others. Decoherence focuses on how quantum systems interact with their environment. In practice, no system is perfectly isolated. Even a single electron is influenced by surrounding fields, particles, and fluctuations. These interactions are often extremely subtle, but they accumulate over time. When a quantum system becomes entangled with its environment, the different components of its superposition begin to lose their ability to interfere with one another. The coherence, which allows for interference effects like those seen in the double-slit experiment, is effectively dispersed into the environment. As a result, the system begins to behave as if it has settled into one of the possible outcomes. From the perspective of an observer who does not have access to all the environmental details, the system appears to have taken on a definite state. This process can happen incredibly quickly. For macroscopic objects, decoherence occurs on timescales so short that superpositions become effectively unobservable. This is one reason why we do not see everyday objects, like chairs or trees, existing in visibly multiple states at once. They are constantly interacting with their environment, and those interactions rapidly suppress any observable quantum coherence. Decoherence provides a powerful explanation for why the classical world appears as it does. It shows how definite outcomes can emerge from underlying quantum processes, without requiring a special role for observation or consciousness. But there is an important detail. Decoherence does not fully solve the measurement problem. It explains how superpositions become effectively hidden, how interference is lost, and how systems begin to behave classically. But it does not explain why a single outcome is realized in any given instance. In other words, decoherence describes how possibilities become separated and non-interfering. It does not explain how one of those possibilities becomes the one that is actually observed. This distinction is subtle, but significant. It means that while decoherence brings us closer to understanding the transition from quantum to classical behavior, it leaves open the question of what ultimately selects the outcome. Different interpretations of quantum mechanics offer different answers to this question. Some suggest that the wave function never truly collapses, and that all outcomes continue to exist in some form, as in the many worlds interpretation. Others propose that collapse is a real physical process, though its mechanism is not yet fully understood. Still others, like cubism or relational quantum mechanics, reinterpret the meaning of the wave function and the role of measurement altogether. What is striking is that all of these interpretations agree on the mathematical predictions of quantum mechanics. They differ in how they describe what is happening behind those predictions. This is why the measurement problem is often described as a problem of interpretation, rather than a problem of calculation. The equations are clear, the experiments are consistent, the outcomes are predictable in terms of probability. But the story we tell about how those outcomes arise is not uniquely determined. In a way, this reflects a deeper aspect of science. There are times when the mathematical structure of a theory becomes so successful that it outpaces our ability to form an intuitive picture of what it represents. The theory works, but the underlying reality it describes does not fit neatly into familiar categories. The measurement problem sits precisely in that space. It invites us to ask whether the concepts we're using, such as state, measurement, and outcome, are the most appropriate ones for describing what is happening at the quantum level. It also encourages a certain humility. The recognition that even with a theory as successful as quantum mechanics, there are still aspects of its meaning that remain open to interpretation. And perhaps that is part of what gives the quantum world its particular kind of mystery. Not a dramatic puzzle waiting for a single solution, but a quiet boundary. A place where our descriptions are precise, our predictions are accurate, and yet our understanding of what it all means is still unfolding. A reminder that explanation itself has limits, and that sometimes those limits are not obstacles, but invitations to look more carefully at the questions we're asking. There is a familiar idea that uncertainty comes from not knowing enough. If you toss a coin and cannot predict whether it will land heads or tails, it feels natural to assume that the uncertainty lies in your lack of information. Perhaps you do not know the exact force of the toss, the angle of release, or the tiny currents of air surrounding it. In principle, if you could measure every detail with perfect accuracy, the outcome would be completely determined. This way of thinking works well for many situations in classical physics. But when we move into the quantum world, uncertainty takes on a different character. It is no longer simply a reflection of incomplete knowledge. It becomes a fundamental feature of how systems are described. This idea is captured in the Heisenberg uncertainty principle, introduced by Werner Heisenberg in the late 1920s. It states that certain pairs of physical properties cannot both be known with arbitrary precision at the same time. The most well-known example involves position and momentum. In clear-spoken form, the principle can be expressed as the uncertainty in position multiplied by the uncertainty in momentum is always greater than or equal to a very small constant related to Planck's constant. This statement is not about the limitations of our instruments. It is about the structure of the theory itself. No matter how carefully a system is prepared, no matter how precise the measurement, there is a limit to how sharply these properties can be defined simultaneously. To understand why this is the case, it helps to look more closely at the wave-like nature of quantum systems. In quantum mechanics, particles such as electrons are described by wave functions, which have properties similar to waves, and waves by their nature have a relationship between how localized they are in space and how well-defined their wavelengths are. Imagine a perfectly regular wave extending infinitely in space. It has a precise wavelength which corresponds to a well-defined momentum. But because it stretches out everywhere, its position is completely uncertain. You cannot say where it is because it is spread across all space. Now imagine the opposite. A very short wave packet tightly localized in a small region. Its position is well defined, but to create that localization, many different wavelengths must be combined. As a result, its momentum becomes uncertain, spread across a range of values. This trade-off is not a flaw. It is a property of waves themselves. Quantum systems inherit this property because they are described by wave functions. The uncertainty principle is, in a sense, a direct consequence of this wave-based description. This means that uncertainty is not something we can eliminate by improving our measurements. It is built into the way reality behaves at small scales. This raises a deeper question. If uncertainty is fundamental, does that mean the universe is truly random? Or is there some hidden structure beneath the probabilities, something that restores determinism at a deeper level? This question has been the subject of ongoing debate. Some physicists accept that quantum mechanics introduces genuine randomness into the fabric of reality. In this view, when a measurement is made, the outcome is not determined by prior conditions. It is selected probabilistically, with no underlying cause that fixes the result in advance. Others have explored the possibility that the randomness is only apparent. E.T. Jaynes, for example, argued that probability should be understood as a measure of incomplete knowledge, even in quantum contexts. From this perspective, the uncertainty in quantum mechanics might reflect hidden variables or deeper structures that are not captured by the standard theory. However, attempts to construct such hidden variable theories face significant challenges, particularly in light of results like Bell's theorem, which place strong constraints on how such theories can behave. Even so, the question remains open in a broader sense. What does it mean for something to be fundamentally uncertain? Is uncertainty a statement about reality itself, or about the limits of how we can describe it. One way to approach this is to consider the role of knowledge. In classical physics, knowledge is, at least in principle, unlimited. If you could gather enough information, you could predict everything. The universe is assumed to be fully knowable, even if we never actually reach that level of understanding. In quantum mechanics, knowledge has built-in limits. There are properties that cannot be simultaneously specified with arbitrary precision. There are outcomes that cannot be predicted with certainty, only with probabilities. These limits are not practical obstacles, but fundamental features of the theory. This suggests that the universe may not be fully knowable in the classical sense. Not because it is disordered or chaotic, but because the structure of reality itself does not allow for complete specification of all properties at once. This idea can feel unusual, because it challenges a deeply rooted assumption. The assumption that, given enough effort and precision, everything could, in principle, be known. Quantum mechanics invites a different perspective. It suggests that there are aspects of reality that are inherently open, not fixed until interactions occur, and not fully describable in terms of definite values. At the same time, this does not mean that the universe is arbitrary or without structure. The probabilities predicted by quantum mechanics are precise and consistent. The uncertainty principle sets clear limits, not vague ones. The behavior of systems follows well-defined mathematical rules, so the picture that emerges is not one of chaos, but of structured uncertainty, a balance between what can be known and what remains open. In a way, this can be seen as a refinement of our understanding of predictability. Instead of asking for exact outcomes, we ask for probability distributions. Instead of expecting complete certainty, we work within well-defined limits, and within those limits, the theory performs with extraordinary accuracy. Perhaps this is part of what makes the uncertainty principle so intriguing. It is not just a statement about measurement, it is a statement about the nature of reality and the nature of knowledge. It tells us that there are boundaries to what can be simultaneously defined, boundaries that arise not from our limitations, but from the structure of the world itself. And in recognizing those boundaries, we begin to see that uncertainty is not simply a lack, it is a feature, a fundamental aspect of how the universe is organized, quietly shaping what can be known and what must remain, at least in part, open. There is a quiet assumption that runs through most of our everyday thinking. Things are separate. A book rests on a table, a glass sits beside it. Each object has its own properties, its own position, its own identity. Even when objects interact, we tend to imagine that they remain fundamentally distinct, carrying their own information independently. This assumption feels so natural that it is rarely questioned. But in the quantum world, there are situations where this idea of separateness begins to dissolve. The phenomenon responsible for this is known as entanglement. Entanglement occurs when two or more quantum systems become linked in such a way that their states can no longer be described independently. Instead of each system having its own separate description, the combined system must be treated as a single unified whole. This is not just a matter of correlation in the usual sense. In classical physics, two systems can be correlated because they share a common history. For example, if you take a pair of gloves and separate them, placing one in each of two boxes, then opening one box immediately tells you what is in the other. If you find a left glove, you know the other box contains a right glove. But in that case, the properties were already determined from the beginning. The gloves had definite identities before they were separated. The correlation reflects a shared origin, not a deeper connection. Quantum entanglement is different. When two particles are entangled, their properties are not fully defined independently before measurement. Instead, the system is described by a single quantum state that includes both particles together. Only when a measurement is made do specific outcomes appear, and those outcomes are correlated in a way that cannot be explained by pre-existing properties alone. To make this more concrete, consider a pair of particles prepared in an entangled state involving their spin. The combined system might be arranged so that the total spin is zero. This means that if one particle is found to have spin up, the other must have spin down, and vice versa. But before measurement, neither particle has a definite spin in the classical sense. The system exists in a superposition of both possibilities, with the outcomes only becoming definite when measurements are made. What makes this particularly striking is that the correlations persist regardless of the distance between the particles. If the particles are separated by a few meters, or even by kilometers, the relationship remains. Measuring one immediately determines the corresponding outcome for the other, even though no signal appears to travel between them in the conventional sense. This aspect of entanglement was famously described by Albert Einstein as spooky action at a distance, reflecting his discomfort with the idea that distant systems could exhibit such strong connections. For many years, this remained a topic of debate. Was entanglement a real feature of the world, or simply a limitation of the theory? This question was addressed through a series of increasingly precise experiments, many of which were led by physicists such as Anton Zeilinger. Zeilinger and his colleagues performed experiments that tested the predictions of quantum mechanics using entangled photons. These experiments involved creating pairs of photons in entangled states and measuring their properties at separate locations. The results consistently matched the predictions of quantum theory. The correlations observed could not be explained by any model in which the particles carried pre-existing, independent properties that determined the outcomes. Instead, the results confirmed that the entangled state itself is fundamental. The system must be treated as a single entity, even when its components are widely separated. This leads to a significant shift in how we think about the structure of reality. If entangled systems cannot be described independently, then the idea that the world is made up of separate, self-contained objects becomes less fundamental. Instead, relationships take on a central role. The properties of a system are not always intrinsic to the system alone. They can depend on how that system is connected to others, how it has interacted, and how it is measured. In this sense, entanglement suggests that the universe is not simply a collection of individual parts, it is a network of relationships. Each part gains its meaning, at least in some contexts, through its connections to others. This perspective aligns with broader developments in quantum theory, where interactions and correlations often play a more fundamental role than isolated entities. In quantum information theory, for example, entanglement is treated as a resource. It can be used for tasks such as quantum teleportation, where the state of a particle is transferred from one location to another using entangled pairs and classical communication. It also plays a role in quantum cryptography, where entangled states can be used to create secure communication channels. These applications demonstrate that entanglement is not just a philosophical curiosity. It has practical consequences and can be harnessed in real technologies. At the same time, its conceptual implications remain profound. It challenges the idea that physical systems can always be understood by analyzing their parts in isolation. Instead, it suggests that, at a fundamental level, the whole can be more than the sum of its parts. Not in a vague or mystical sense, but in a precise, mathematically defined way. The state of the whole system contains information that cannot be fully captured by considering each component separately. This shift from objects to relationships can feel subtle, but it represents a deep change in perspective. It encourages us to think less in terms of isolated things and more in terms of connections and interactions. Less in terms of independent properties, and more in terms of shared structures. And perhaps this is part of why entanglement feels so mysterious. It does not simply add a new feature to our understanding of the world. It invites us to reconsider the very idea of separateness, to recognize that at the smallest scales the boundaries we draw between systems may not always reflect how reality is organized. Instead of a collection of distinct pieces, the quantum world reveals something more interconnected. A structure where relationships are not just secondary but essential. And in that quiet shift, from separation to connection, the sense of mystery deepens. Not because the theory is unclear, but because it reveals a way of being that is different from what we're used to imagining. There is a quiet set of assumptions that has guided physics for centuries. They are so natural that they rarely feel like assumptions at all. The first is realism, the idea that physical systems possess definite properties, whether or not we observe them. A particle has a position, a spin, a state, and those properties exist independently of measurement. The second is locality, the idea that objects are only directly influenced by their immediate surroundings. If something happens in one place, it cannot instantly affect something far away without some form of signal traveling between them, and that signal cannot move faster than the speed of light. Together, these ideas form what is often called local realism. They are deeply intuitive, they align with everyday experience. They also sit comfortably within the framework of classical physics, and even within Einstein's theory of relativity. But quantum mechanics, particularly through the phenomenon of entanglement, begins to place pressure on this combination. For many years, it was unclear whether this tension reflected a genuine feature of reality or simply an incomplete understanding. Perhaps, as Einstein suspected, there were hidden variables, additional pieces of information not included in quantum theory that would restore both realism and locality, preserving the familiar structure of cause and effect. In the 1960s, a physicist named John Bell approached this question in a new way. Rather than arguing philosophically, he asked whether it was possible to design an experiment that could distinguish between quantum mechanics and any theory that preserved local realism. Bell derived a set of constraints, now known as Bell inequalities. These inequalities describe the maximum strength of correlations that can exist between two systems if both locality and realism hold true. The details of these inequalities involve careful statistical reasoning, but the core idea is surprisingly simple. If two particles carry predetermined properties, and if no influence can travel between them faster than light, then the correlations between measurements made on those particles must fall within certain limits. Quantum mechanics, however, predicts correlations that exceed those limits. This means that if experiments confirm the quantum predictions, then at least one of the assumptions, locality or realism, must be abandoned. This was a remarkable proposal. It turned a philosophical debate into an empirical question, one that could be tested in the laboratory. Over the following decades, a series of increasingly refined experiments were carried out to test Bell's inequalities. Among the most influential were those conducted by Alain Aspect and his team in the early 1980s. Aspect's experiments involved pairs of entangled photons emitted in such a way that their polarization states were correlated. The photons were sent to separate detectors, where measurements could be made along different orientations. Crucially, the choice of measurement settings was varied rapidly, ensuring that no signal traveling at or below the speed of light could coordinate the outcomes between the two detectors. The results were clear. The correlations observed in these experiments violated Bell's inequalities. They matched the predictions of quantum mechanics, not those of any theory based on local realism. Since then, many additional experiments have been performed, with increasing levels of precision and control. These include experiments that close various loopholes, ensuring that the results cannot be explained by hidden biases or experimental imperfections. Research groups across the world, including those led by Anton Zeilinger and others, have confirmed these findings repeatedly. The conclusion is difficult to avoid. The combination of locality and realism, as traditionally understood, cannot both be correct. At least one of these assumptions must give way. This realization marks a profound turning point in our understanding of reality. If we choose to preserve realism, then we must accept that influences can act in ways that are not confined by the usual notion of locality. This does not necessarily mean faster than light signals in the traditional sense, but it does suggest that the connections between systems can transcend spatial separation in a way that classical physics does not allow. If, on the other hand, we choose to preserve locality, then we must give up the idea that physical properties exist independently of measurement. In this case, the act of measurement plays a more fundamental role in defining the state of a system. Different interpretations of quantum mechanics take different paths. Some, like the many worlds interpretation, avoid the need for faster-than-light influences by suggesting that all outcomes occur in a branching structure of realities, preserving a kind of locality at the cost of introducing a vast multiplicity of worlds. Others, like certain relational or informational interpretations, question the assumption of realism, proposing that properties are not absolute, but arise through interactions. What is striking is that none of these options fully restores the comfortable picture provided by classical physics. Something has to change, and that change is not a small adjustment, but a shift in how we think about the structure of the world. One way to understand the significance of this is to reflect on what locality and realism represent. Locality is closely tied to the idea of causality, the principle that causes precede effects and that influences propagate through space over time. It provides a sense of order and continuity, ensuring that events are connected in a coherent way. Realism, on the other hand, supports the idea that the world exists independently of observation. It allows us to think of physical systems as having definite properties, regardless of whether they are being measured. Bell's theorem shows that we cannot hold on to both of these ideas in their classical forms. The universe, at its most fundamental level, does not fully conform to this combined picture. This does not mean that causality disappears or that the world becomes arbitrary. Quantum mechanics remains a highly structured and predictive theory. The correlations it describes are precise and consistent. The outcomes follow well-defined probability distributions, but the underlying framework is different. It suggests that either the connections between distant systems are more subtle than classical locality allows, or that the properties of systems are not fully defined until interactions occur. Perhaps both ideas need to be reconsidered. In a quiet way, this shifts the focus from isolated objects to relationships and correlations. It suggests that the behavior of a system cannot always be understood by looking at it alone, but must be considered in the context of how it is connected to others, and in doing so it deepens the sense of mystery, not because the theory is incomplete, but because it reveals that some of our most basic assumptions about the world may not apply at the smallest scales. The universe is still lawful, still consistent, still understandable through careful observation and mathematical description. But the picture it presents is less familiar, less anchored in the idea of separate, independent objects, and more reflective of a reality where connections, correlations, and relationships play a central role. A reality where the boundaries between things are not always as clear as they first appear, and where understanding requires not just new equations, but a willingness to rethink what it means for something to exist, to influence, and to be known. Time has a quiet way of guiding how we understand everything. It gives events their order. It tells us what comes before and what comes after. Causes lead to effects, and those effects unfold into new causes, creating a steady flow that feels as natural as breathing. If you drop a glass, it falls and breaks. The breaking does not cause the fall. The sequence is clear, and it always moves in one direction. This sense of order is so deeply embedded in our experience that it feels almost impossible to imagine otherwise. But as with many things in the quantum world, this familiar structure begins to soften when we look more closely. In classical physics, causality is straightforward. The state of a system at one moment determines its state at the next. Information flows forward in time. Signals propagate through space at finite speeds, limited by the speed of light, as described in Einstein's theory of relativity. Everything fits together into a consistent picture, where the past shapes the future, but not the other way around. Quantum mechanics introduces a more subtle situation. The mathematical framework itself, particularly the Schrödinger equation, is time-symmetric. This means that at a fundamental level, the equations do not distinguish between past and future. They work equally well if time moves forward or backward, and yet our experience is not time-symmetric. We remember the past, not the future. We see causes leading to effects, not effects leading to causes. There is a clear direction to time in everyday life, often referred to as the arrow of time. This difference raises an interesting question. If the underlying laws are time-symmetric, where does the direction of time come from? One possible answer lies in thermodynamics, where the second law states that entropy, a measure of disorder, tends to increase over time. This provides a statistical explanation for why processes appear to move in one direction. But quantum mechanics adds another layer to the discussion. There are experiments that seem to blur the distinction between past and future in ways that challenge classical intuition. One of the most intriguing examples comes from John Archibald Wheeler, who proposed what are known as delayed choice experiments. In these experiments, a particle such as a photon passes through an apparatus that can be configured in different ways. Depending on the configuration, the photon can behave as if it has taken one path or multiple paths simultaneously. The surprising feature is that the choice of how to measure the photon can be made after the photon has already entered the apparatus. In some versions of the experiment, this choice is made so late that, from a classical perspective, it seems as though the photon would have had to decide how to behave before the measurement setup was determined, and yet the results consistently match the predictions of quantum mechanics. The photon behaves in a way that is consistent with the measurement that is ultimately performed, even if that measurement choice is delayed. This does not mean that the future is literally changing the past in a simple sense, but it does suggest that the way we assign definite histories to quantum systems is not as straightforward as we might expect. The idea that a particle has a single, well-defined path through space, independent of how it is measured, becomes difficult to maintain. Instead, the description of the system appears to depend on the entire experimental context, including choices made at later times. This leads to more speculative ideas about the nature of causality. One such idea is retrocausality, which has been explored by philosophers and physicists such as Hugh Price. Retrocausality suggests that influences might, in some sense, travel backward in time, allowing future events to affect past states. This does not imply a reversal of time in the everyday sense, nor does it lead to paradoxes like changing historical events. Rather, it proposes that the fundamental relationships between events may not be strictly one-directional. In certain interpretations, the correlations observed in quantum experiments could be explained by allowing influences that connect past and future in a more symmetric way. While this idea remains controversial, it highlights an important point. Our usual assumptions about causality may not be the only way to understand the structure of events. Another perspective is that time itself may not be fundamental. In some approaches to quantum gravity, including work by Carlo Rovelli and others, time is treated as an emergent property rather than a basic ingredient of the universe. In this view, the fundamental description of reality does not include a global clock ticking uniformly for all systems. Instead, time arises from the relationships between different parts of the system, from changes and interactions that give rise to a sense of sequence. This idea can feel abstract, but there are hints of it even within standard quantum mechanics. For example, the way we describe a system often depends on how it is compared to another system. Without a reference, the notion of time can become less well defined. Similarly, in certain quantum experiments, the order of events can appear ambiguous. There are situations studied in quantum information theory where the sequence of operations does not have a definite order. Instead, processes can exist in a superposition of different causal orders, meaning that it's not strictly meaningful to say which event happened first. These ideas are still being actively explored, but they point toward a broader possibility. That time, like many other familiar concepts, may not be as fundamental as it seems. It may emerge from deeper structures, just as classical behavior emerges from quantum systems. All of this contributes to a growing sense that the relationship between time and causality is more subtle than classical physics suggests. The universe still exhibits regularities, causes still appear to lead to effects, signals still respect the speed of light in the sense required by relativity. But beneath this familiar structure there may be a more flexible framework, one in which the assignment of definite histories depends on context, where the distinction between past and future is not always absolute, and where the flow of time itself may arise from deeper interactions. This does not mean that time becomes meaningless. It remains an essential part of how we describe and experience the world. But it does suggest that our intuitive picture of time as a fixed universal background may not capture the full story, and perhaps this is another reason the quantum world feels so mysterious, because it does not simply challenge our understanding of objects or properties. It gently invites us to reconsider something even more fundamental: the way events are ordered, the way causes and effects are connected, and the quiet assumption that time itself flows in a single, unambiguous direction. In exploring these ideas, we're not just learning about particles or fields. We're exploring the structure of reality at a level where even time may not be what it seems. By this point, the mathematics of quantum mechanics is not in doubt. It works with extraordinary precision. It predicts experimental outcomes to levels of accuracy that are difficult to overstate. In some cases, agreement between theory and experiment reaches more than 10 decimal places, a level of precision that is rarely matched in any other area of science. And yet, despite this success, there is a quiet and persistent question. What does it all mean? The equations tell us how to calculate probabilities. They describe how systems evolve and how measurements relate to outcomes. But they do not provide a single, unambiguous picture of what is happening beneath those calculations. As a result, physicists have developed a range of interpretations. Each interpretation offers a way of understanding the same mathematical framework. They agree on the predictions. They differ in how they describe the underlying reality. One of the earliest and most influential interpretations is the Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg. The Copenhagen interpretation takes a pragmatic approach. It suggests that quantum mechanics does not describe an underlying reality in the classical sense. Instead, it provides a set of rules for predicting the outcomes of measurements. The wave function represents our knowledge or are a description of the system rather than a direct physical entity. In this view, questions about what a system is doing between measurements are considered less meaningful. What matters are the observable outcomes and the probabilities associated with them. When a measurement occurs, the wave function is said to collapse, meaning that the range of possibilities is reduced to a single outcome. The Copenhagen interpretation does not attempt to describe the mechanism of this collapse in detail. It accepts it as part of the framework, focusing instead on the practical success of the theory. This approach has been widely used because it aligns closely with how experiments are conducted and how predictions are made. However, not everyone finds it satisfying. Some physicists have sought interpretations that provide a more detailed account of what is happening, even if that account is more abstract. One such interpretation is the many worlds interpretation, originally proposed by Hugh Everett in the late 1950s and later developed further by physicists such as David Deutsch. The many worlds interpretation takes the mathematics of quantum mechanics at face value, without introducing wave function collapse. Instead, it suggests that all possible outcomes described by the wave function actually occur. When a measurement is made, the universe does not select a single result. Instead, it branches into multiple versions, each corresponding to a different outcome. In one branch, a particle might be found in one state. In another branch, it is found in a different state. Each branch evolves independently, and observers within each branch experience a single, definite outcome. From this perspective, the apparent randomness of quantum mechanics arises because we find ourselves in one particular branch without access to the others. This interpretation removes the need for collapse and preserves the deterministic evolution described by the Schrödinger equation. But it comes with its own conceptual challenges. It implies the existence of an enormous number of parallel realities, each representing a different outcome of quantum events. While this idea is mathematically consistent, it can feel difficult to reconcile with everyday experience. Another approach, quite different in character, is Bohmian mechanics, developed by David Bohm in the 1950s. Bohmian mechanics introduces the idea of hidden variables. In this framework, particles have definite positions and trajectories at all times, guided by a mathematical entity known as the pilot wave. The wave function still evolves according to the usual equations, but it acts as a guiding field that influences the motion of particles. This restores a form of determinism. Given the initial conditions, the future behavior of the system is fully determined. The apparent randomness arises from our lack of knowledge about the precise initial state. However, Bohmian mechanics comes at a cost. It requires non-local interactions, meaning that the behavior of one particle can depend instantaneously on the state of another, regardless of the distance between them. This is consistent with the results of Bell's theorem, but it challenges the classical idea of locality. It also introduces additional structure beyond the standard formulation of quantum mechanics, which some physicists view as less economical. A more recent and more controversial idea is superdeterminism, explored by physicists such as Gerard 't Hooft. Superdeterminism takes a different approach to the challenges posed by Bell's theorem. Instead of abandoning locality or realism, it questions an assumption that is often taken for granted in experiments, namely the independence of measurement settings. In most experimental designs, it is assumed that the choices of how to measure a system are independent of the properties of the system itself. Superdeterminism suggests that this independence may not hold. In this view, the state of the universe could be such that the measurement settings and the properties of the particles are correlated in a way that preserves local realism. This would mean that the apparent violations of Bell's inequalities do not require non-local influences, but arise from deeper, pre-existing correlations. While this idea is logically consistent, it is often met with skepticism. One reason is that it seems to require a level of coordination in the universe that feels highly constrained. The initial conditions would need to be arranged in such a way that all future measurement choices are correlated with the systems being measured. This can give the impression of a universe that is finely tuned in a way that is difficult to test or falsify. Despite these challenges, superdeterminism remains an active area of research, illustrating how open the question of interpretation still is. Across all of these approaches, one thing remains consistent. The predictions of quantum mechanics do not change. Whether one adopts the Copenhagen interpretation, many worlds, Bohmian mechanics, or superdeterminism, the calculated probabilities for experimental outcomes remain the same. This is a key point. The differences between interpretations lie in their explanations, not in their predictions. They offer different ways of understanding the same underlying mathematics. This situation is somewhat unusual in science. Typically, competing theories can be distinguished by their predictions. Experiments can confirm one and rule out others. In the case of quantum mechanics, many interpretations are empirically equivalent, at least with current technology. This means that the choice between them often depends on broader considerations: conceptual clarity, philosophical preferences, ideas about simplicity, determinism, or the nature of reality. Some physicists prefer interpretations that minimize additional assumptions. Others are drawn to those that provide a more detailed picture, even if it is more complex. There is no universal agreement, and perhaps that is part of what makes this topic so fascinating. The mathematics of quantum mechanics provides a clear and reliable guide to what we will observe. But when we ask what is really happening, the answers become more varied, not because the theory is incomplete in its predictions, but because it leaves room for multiple ways of understanding its meaning. In a quiet way, this reflects a deeper aspect of science. That understanding is not only about calculation, but also about interpretation, about how we connect mathematical structures to ideas about reality. And in the case of quantum mechanics, that connection remains open, not as a flaw, but as an invitation to explore different perspectives, to question assumptions, and to recognize that even our most successful theories may leave space for multiple ways of seeing the world. There is a quiet shift that has been taking place in physics over the past several decades. It is not a single discovery or a single equation, but a gradual change in how we think about what the universe is made of. For a long time, the focus was on matter and energy. Particles, fields, forces. These were the primary ingredients. Physics aimed to describe how these entities behave, how they interact, and how they give rise to the structures we observe. But as quantum theory developed, another concept began to move closer to the center: information. At first, information might seem like an abstract idea, something associated with communication, computation, or human knowledge. But in modern physics, information is treated as something much more concrete. It has measurable properties, it obeys physical laws, and it appears to play a fundamental role in how systems evolve. This shift can be traced in part to the work of John Archibald Wheeler, who proposed the phrase, "it from bit." Wheeler's idea was that every physical quantity, every particle, every field ultimately arises from binary choices, from yes or no answers to fundamental questions. In this view, the fabric of reality is not built from objects alone, but from information about those objects. Rather than asking only what things are, Wheeler encouraged asking what can be known about them, and how that knowledge is structured. This perspective gained momentum with the development of quantum information theory. Quantum information theory takes the principles of quantum mechanics and applies them to the processing and transmission of information. It studies how quantum systems can store, manipulate, and communicate information in ways that differ from classical systems. One of the key ideas in this field is the quantum bit, or qubit. A classical bit can be either 0 or 1. A qubit, by contrast, can exist in a superposition of both 0 and 1 at the same time. This allows for new kinds of computation and communication, where multiple possibilities can be explored simultaneously. Entanglement, which we explored earlier, plays a central role here as well. Entangled qubits can share information in ways that have no classical equivalent. This enables protocols such as quantum teleportation, where the state of a system is transferred from one location to another without moving the system itself in the usual sense. These developments suggest that information is not just a passive description of physical systems, it is an active ingredient in how those systems behave. Seth Lloyd, a physicist and pioneer in quantum computing, has taken this idea even further. He has proposed that the universe itself can be understood as a kind of quantum computer. In this view, every interaction between particles can be seen as a computation, a transformation of information. The evolution of the universe is then a sequence of computational steps, processing information according to the laws of physics. Lloyd has even estimated the total number of operations that the observable universe could have performed since its beginning. Based on the energy available and the limits set by quantum mechanics, he suggested that the universe has carried out on the order of 10 raised to the 120 operations. This is an unimaginably large number, but it provides a way of thinking about the universe not just as a collection of objects, but as an ongoing process of information processing. Another key concept in this discussion is entropy. In thermodynamics, entropy is often described as a measure of disorder, but in information theory, entropy has a more precise meaning. It measures the amount of uncertainty or the number of possible configurations a system can have. Claude Shannon, the founder of information theory, defined entropy in terms of probabilities. In clear-spoken form, the idea can be expressed as entropy is equal to the negative sum of each probability multiplied by the logarithm of that probability. This definition connects directly to the idea of information. A system with high entropy has many possible states, and therefore contains more uncertainty. A system with low entropy has fewer possibilities and is more ordered. In physics, entropy is not just an abstract quantity. It has real, measurable effects. One of the most intriguing examples comes from the study of black holes. In the 1970s, Jacob Bekenstein proposed that black holes should have entropy. This was a surprising idea, because black holes were traditionally thought of as simple objects, characterized only by their mass, charge, and angular momentum. Bekenstein suggested that the entropy of a black hole is proportional to the area of its event horizon, the boundary beyond which nothing can escape. In clear-spoken terms, the relationship can be expressed as the entropy of a black hole is proportional to the area of its event horizon, divided by a fundamental unit related to Planck's constant, the speed of light, and the gravitational constant. This idea was later supported by Stephen Hawking's discovery that black holes emit radiation, now known as Hawking radiation. Together, these results imply that black holes are not just gravitational objects, but thermodynamic systems with well-defined entropy and temperature. Perhaps even more striking is the implication that the amount of information contained within a region of space may be related to its surface area, rather than its volume. This idea is closely connected to the holographic principle, developed by Gerard 't Hooft and Leonard Susskind. The holographic principle suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram encodes a three-dimensional image on a two-dimensional surface. If this is true, it would mean that the fundamental description of the universe might not require three-dimensional space in the way we usually store it. Instead, the information that defines reality could be stored on lower dimensional structures, with the familiar world emerging from that underlying information. Taken together, these ideas point toward a remarkable possibility. That information is not just a tool we use to describe the universe. It may be what the universe is made of. This does not mean that particles and fields disappear. Rather, it suggests that they may be manifestations of deeper informational structures. The properties we observe, such as position, momentum, and energy, could be ways of encoding and transforming information. In this sense, reality becomes less about objects and more about relationships, patterns, and processes of information exchange. The universe, viewed this way, is not just a stage where events happen. It is an active system, continuously processing, transforming, and encoding information at every scale. This perspective does not resolve all the mysteries of quantum mechanics, but it offers a different way of framing them. Instead of asking only what things are, it invites us to ask what information is available, how it is structured, and how it changes through interactions. And perhaps, in doing so, it brings us a little closer to understanding why the quantum world feels so unusual. Because if reality is fundamentally informational, then the concepts we use to describe it, objects, properties, even space and time, may be secondary, emerging from something deeper, something less tangible, but no less real. A foundation built not from solid pieces but from patterns of information, quietly shaping everything we observe. There is a quiet tension at the heart of modern physics. Two of its most successful theories describe the universe with extraordinary accuracy, yet they do not fit together. On one side, there is quantum mechanics, which governs the behavior of the very small. It describes atoms, particles, and fields with remarkable precision, capturing the probabilistic and often counterintuitive nature of the microscopic world. On the other side, there is general relativity, developed by Albert Einstein, which describes gravity and the large-scale structure of the universe. It explains how massive objects curve space-time, how planets orbit stars, and how galaxies evolve. Each theory works beautifully within its domain. Quantum mechanics excels at small scales. general relativity excels at large scales. But when we try to apply both theories at once, in situations where gravity and quantum effects are both significant, the descriptions begin to break down. This happens in some of the most extreme environments in the universe, near the center of black holes, where gravity becomes incredibly strong. In the earliest moments after the Big Bang, when the universe was both extremely dense and extremely small. In these regimes, we need a theory of quantum gravity, a framework that combines the principles of quantum mechanics with a geometric description of spacetime provided by general relativity. Despite decades of effort, such a theory remains incomplete. This is not for lack of trying. Some of the most brilliant physicists have devoted their work to this problem, developing different approaches that aim to bridge the gap. One of these approaches is loop quantum gravity, associated with researchers such as Carlo Rovelli. Loop quantum gravity builds on the idea that spacetime itself may be quantized. Instead of treating space as a smooth, continuous fabric, it proposes that space is composed of discrete units, often described as loops or networks. These structures form what is sometimes called a spin network, a kind of underlying scaffold that gives rise to the geometry of space. In this framework, areas and volumes are not infinitely divisible. They come in discrete amounts, much like energy levels in quantum mechanics. Time, too, may be discrete, or at least not fundamental in the usual sense. What is particularly interesting about loop quantum gravity is that it does not begin by assuming a background spacetime. Instead, spacetime itself emerges from the relationships between these fundamental elements. This aligns with earlier ideas about discreteness and relational structure, suggesting that space and time are not fixed stages on which events unfold, but products of deeper interactions. Another major approach is string theory, which has been developed extensively by physicists such as Edward Witten. String theory takes a different path. Instead of treating particles as point-like objects, it proposes that the fundamental constituents of the universe are tiny, vibrating strings. These strings can oscillate in different ways, and each pattern of vibration corresponds to a different particle. For example, one mode of vibration might correspond to an electron, another to a photon, and so on. One of the remarkable features of string theory is that it naturally includes gravity. In certain formulations, one of the vibrational modes of the string behaves like a particle called the graviton, which would mediate the gravitational force. This makes string theory a candidate for a unified theory, capable of describing all fundamental interactions within a single framework. However, string theory comes with its own challenges. It often requires additional spatial dimensions beyond the familiar 3, sometimes as many as 10 or 11 in total. These extra dimensions are typically assumed to be compactified, meaning they are curled up at scales far too small to observe directly. While the mathematics of string theory is rich and highly developed, direct experimental evidence remains elusive. Both loop quantum gravity and string theory offer valuable insights, but neither has yet provided a complete and experimentally confirmed theory of quantum gravity. At the same time, new ideas have emerged that suggest the solution may involve rethinking some of our most basic assumptions. One of these ideas is the holographic principle, developed by Gerard 't Hooft and Leonard Susskind. The holographic principle proposes that the information contained within a volume of space can be described entirely by information encoded on its boundary. This idea arose from studies of black hole entropy, particularly the work of Jacob Bekenstein and Stephen Hawking, which showed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. If this principle applies more generally, it suggests that our familiar three-dimensional world may be, in some sense, a projection of information defined on a lower dimensional surface. This does not mean that the world is an illusion, but it does imply that the fundamental description of reality may be very different from the way it appears. Closely related to this is the idea that space-time itself may be emergent. In this view, space and time are not fundamental ingredients of the universe, but arise from more basic structures, such as quantum entanglement or informational relationships. Some researchers have explored how patterns of entanglement could give rise to the geometry of space-time, effectively building space from quantum connections. This is a striking reversal of the usual perspective. Instead of particles existing within space, space itself becomes something that emerges from the relationships between particles. Time, similarly, may arise from the ordering of events within these relationships, rather than existing as a universal background. These ideas are still under active investigation, and many details remain uncertain, but they point toward a common theme, that the familiar concepts of space, time, and geometry may not be the deepest layer of reality. Instead, they may be effective descriptions that emerge at larger scales, much like temperature emerges from the motion of many particles, even though individual particles do not have a temperature in the same sense. This places us at the edge of current understanding, a place where the theories we have are extraordinarily powerful, yet not fully unified, where new ideas are being explored, but definitive answers have not yet been reached. It is a frontier in the truest sense, not defined by a single discovery, but by a collection of questions that push the limits of what we can currently describe. And perhaps this is where the sense of mystery becomes most pronounced, not because we have failed to understand what is already known, but because we are approaching the boundaries of what can be known with existing frameworks. The quantum world, when combined with gravity, does not simply challenge specific ideas. It challenges the foundations on which those ideas are built. It invites us to consider that space and time themselves, the very stage on which all events occur, may be part of a deeper story, one that is still unfolding. And as we look toward that deeper level, the quiet realization emerges that the more we learn, the more the universe reveals not just answers, but new and subtle questions, waiting patiently at the edge of understanding. For all the strangeness we have explored, there is something equally remarkable that often goes unnoticed. The world feels normal. Objects remain in place. Causes lead to effects. A cup sits on a table without slipping into a blur of possibilities. A planet follows a steady orbit rather than dissolving into a cloud of probabilities. Despite everything quantum mechanics tells us about uncertainty, superposition, and entanglement, our everyday experience remains stable, predictable, and reassuringly classical. This raises an important question. If the underlying rules of reality are quantum, why does the world we experience not look quantum? The answer lies in a concept known as emergence. Emergence refers to the idea that complex systems can exhibit behavior that is not immediately obvious from the properties of their individual components. When many parts interact together, new patterns and regularities can arise, patterns that feel stable and predictable, even if the underlying elements are not. A simple example can be found in temperature. An individual molecule does not have a temperature in the usual sense. It has energy, it moves, it interacts. But temperature emerges as a collective property when large numbers of molecules are considered together. It reflects the average motion of countless particles, smoothing out individual variations into a stable, measurable quantity. In a similar way, the classical world emerges from quantum systems. At the level of individual particles, behavior is governed by probabilities and superpositions. But when many particles interact, especially in large complex systems, those quantum features become less visible. One of the key mechanisms behind this transition is decoherence. As discussed earlier, decoherence occurs when a quantum system interacts with its environment. These interactions cause the different components of a superposition to lose coherence, meaning they no longer interfere with one another in observable ways. In practice, this happens extremely quickly. Consider an object the size of a grain of dust, containing roughly 10 raised to the 15 atoms. Each of those atoms is interacting with surrounding particles, photons, and fields. The number of interactions is enormous, and they occur on timescales that are incredibly short. As a result, any quantum superpositions involving the position or state of the dust particle are effectively suppressed almost instantly. The system begins to behave as if it has a definite position and a definite state, even though, at a deeper level, it is still governed by quantum laws. This process creates the appearance of classical behavior, not by eliminating quantum effects, but by making them inaccessible at larger scales. Scale plays a crucial role here. At very small scales, such as individual electrons or photons, quantum effects are prominent. Superposition, interference, and entanglement can be observed directly. At larger scales, involving vast numbers of particles, these effects become increasingly difficult to detect. The complexity of the system acts as a kind of filter, smoothing out the underlying quantum behavior into stable classical patterns. This idea was captured elegantly by physicist Philip Anderson in his essay titled "More is Different." Anderson argued that as systems grow in size and complexity, new levels of organization emerge that cannot be fully understood by simply analyzing their smallest components. In other words, knowing the laws that govern individual particles is not always sufficient to predict the behavior of large systems. New principles, new patterns, and new regularities arise at each level of complexity. This perspective helps explain why the classical world feels so distinct from the quantum one. It is not that quantum mechanics stops applying at larger scales. It is that the collective behavior of many interacting components gives rise to new effective laws that describe the system at that scale. These effective laws are simpler, more stable, and more intuitive than the underlying quantum description. They allow us to treat objects as having definite positions, definite velocities, and well-defined properties, even though, at a deeper level, those properties are rooted in probabilities and interactions. Stability is another key factor. In the quantum world, individual systems can be highly sensitive to small changes, but in large systems, stability often emerges through redundancy and averaging. For example, a solid object maintains its shape because of the collective interactions of its atoms bound together in a stable structure. Small fluctuations at the atomic level do not significantly alter the overall form. Similarly, when you place a book on a table, its position is defined by the combined behavior of an enormous number of particles. The uncertainties at the microscopic level are present, but they are so small and so averaged out that they become negligible at the scale of everyday experience. This creates what might be called the illusion of certainty. Not an illusion in the sense that it is false, but in the sense that it is an emergent property. The certainty we perceive is real at our scale, even though it arises from underlying processes that are not themselves certain in the same way. This layered structure of reality allows different descriptions to coexist. At one level, quantum mechanics provides the fundamental rules. At another level, classical physics offers an effective description that is easier to use and aligns with our intuition. Both are valid within their domains. Both capture important aspects of how the world behaves, and both are necessary for a complete understanding. This idea of emergence connects directly to everyday experience. When you watch a wave moving across the surface of water, you do not think about the motion of individual molecules. You see a coherent pattern, a smooth and continuous form that emerges from countless interactions. In the same way, the classical world we experience is a pattern that emerges from the underlying quantum processes. It feels solid, stable, and predictable because of the scale and complexity involved. And perhaps this is why the quantum world feels so mysterious. Not because it replaces the familiar world, but because it underlies it. It is always there, shaping the behavior of matter and energy, even when its effects are not directly visible. The stability of everyday life does not contradict quantum mechanics. It is a consequence of it, a natural outcome of how complex systems behave when built from quantum components. And in recognizing this, a quiet balance begins to emerge between the uncertainty of the microscopic world and the certainty of the macroscopic one, between possibility and stability, between the deeper structure of reality and the way it appears to us, a reminder that what feels simple and obvious is often the result of layers of complexity, working together in ways that are not immediately visible, but quietly present in everything we experience. There is a quiet expectation we carry with us, often without noticing, that the world should make sense, not just mathematically, but intuitively, that if something is explained clearly enough, we should be able to picture it, to feel it as reasonable, to connect it to everyday experience, and when that does not happen, when an idea resists intuition, it can feel as though something has gone wrong. But in the case of quantum physics, that feeling may be pointing in a different direction, not toward a failure of understanding, but toward the limits of how our minds are built to understand. Human intuition did not evolve to grasp the behavior of electrons, photons, or quantum fields. It evolved for survival, for navigating environments filled with medium-sized objects, moving at relatively slow speeds, under conditions where classical physics provides an excellent approximation of reality. Our ancestors needed to judge distances, anticipate motion, recognize patterns, and respond quickly to changes in their surroundings. These abilities were shaped over millions of years by natural selection, refining the brain to handle the kinds of problems that were most relevant to survival. As a result, our intuitive understanding of the world is deeply tuned to a specific scale. We are comfortable with objects that have definite positions, definite boundaries, and predictable behavior. We expect causes to produce effects in a clear sequence. We assume that things are either here or there, not both at once. These expectations are not arbitrary. They reflect the regularities of the environment in which human cognition developed, but they are not universal truths, they are adaptations. Donald Hoffman, a cognitive scientist, has explored this idea through what he calls the interface theory of perception. According to Hoffman, our perception of the world is not a direct window into objective reality. Instead, it is more like a user interface, designed to present information in a way that is useful for survival, rather than accurate in every detail. A simple analogy is the desktop interface of a computer. When you see an icon representing a file, you are not seeing the underlying structure of bits and electrical states. You are seeing a simplified representation that allows you to interact with the system efficiently. In the same way, our sensory experience may present a simplified, stable version of reality, one that hides much of the underlying complexity. From this perspective, it is not surprising that quantum mechanics feels unintuitive. The quantum world lies far outside the range of conditions that shaped our perception. It operates at scales and under rules that our brains were never designed to visualize directly. This helps explain why certain quantum concepts feel particularly difficult. Superposition challenges the idea that a system must be in a single, definite state. Entanglement challenges the idea that systems are independent. The uncertainty principle challenges the idea that properties can be precisely defined at all times. Each of these ideas conflicts with deeply ingrained patterns of thought, and those patterns are not easily adjusted. There are also specific cognitive biases that reinforce these expectations. One of them is a preference for determinism. We tend to assume that events have clear causes and predictable outcomes. This bias helps in everyday reasoning, where understanding cause and effect is essential. But it can make probabilistic descriptions feel incomplete or unsatisfying, even when they are fundamentally accurate. Another bias is the preference for continuity. We expect changes to occur smoothly, without sudden jumps or discrete steps. This aligns with our experience of motion and transformation at larger scales. But it can make the quantized nature of energy and the existence of discrete states feel unnatural. There is also a tendency to think in terms of objects. We naturally categorize the world into things, separate entities with boundaries and identities. This makes it easier to navigate and interact with our environment. But in quantum physics, where fields, processes, and relationships take center stage, this object-based thinking can become limiting. These biases are not flaws. They are features of a system that has been highly optimized for a particular set of conditions. But when we step outside those conditions, when we explore the quantum world, they can lead to confusion. This is why even experienced physicists sometimes describe quantum mechanics as counterintuitive. The mathematics can be clear, the predictions can be precise, but the mental image, the intuitive picture, often remains elusive. And that is not necessarily a problem. It may simply reflect the fact that intuition has limits. There are domains of reality where understanding does not come from visualization or everyday reasoning, but from mathematical structure and careful experimentation. In these domains, clarity does not always feel like familiarity. It may feel abstract, or even slightly unsettling, because it does not align with the patterns we're used to. Recognizing this can be helpful. It allows us to shift our expectations. Instead of asking why quantum mechanics does not feel intuitive, we can ask why we would expect it to be intuitive in the first place. Given how our minds have evolved, it would be more surprising if it did feel natural. In this sense, confusion is not a sign of failure. It is a sign that we are encountering something that lies beyond the range of everyday experience. Something that requires new ways of thinking, new tools, and perhaps a different relationship between understanding and intuition. And there is a certain quiet reassurance in that, because it suggests that the difficulty is not with the theory alone, but with the interface through which we are trying to understand it. Our perception, our intuition, our mental models, they are all part of the process. But they are not the final authority on what is real. As we continue to explore the quantum world, we may not always be able to picture it in the way we picture familiar objects, but we can still understand it, not through intuition alone, but through a combination of mathematics, experiment, and careful reasoning. And perhaps, over time, a new kind of intuition begins to form, one that is less tied to everyday experience and more aligned with the deeper structure of reality, a quieter, more flexible way of understanding. one that accepts that the universe does not have to feel familiar in order to be true. There is something quietly unusual about the way physicists talk about quantum mechanics, not about how they calculate. On that front, there is remarkable agreement. The equations are well established. The predictions are precise. Experiments, from particle accelerators to delicate quantum optic setups, consistently confirm the theory's results. Whether one is working at a laboratory like CERN or in a university research group, the mathematical framework is the same. But when the conversation turns to what the theory actually means, something changes. The certainty softens. Different physicists, often equally experienced and equally familiar with the mathematics, begin to describe the same theory in different ways. Some speak in terms of wave function collapse. Others talk about branching worlds. Some emphasize information and knowledge, while others focus on hidden variables or relational properties. It can feel surprising at first. How can there be so much agreement on the calculations, and yet so much variation in interpretation? To understand this, it helps to distinguish between two kinds of understanding. The first is operational. Operational understanding focuses on what the theory allows us to do. It tells us how to calculate probabilities, how to design experiments, and how to predict outcomes. Quantum mechanics excels in this regard. It provides a clear set of rules that can be applied consistently, leading to reliable results. The second is conceptual. Conceptual understanding asks what those rules are describing. What is the nature of the wave function? What happens during measurement? Are the probabilities fundamental, or do they reflect something deeper? It is in this second domain that disagreement arises. Over the years, physicists have even attempted to measure these differences more formally. Surveys conducted at conferences on quantum foundations, such as those organized in places like Vienna, have asked participants which interpretation they prefer. The results show a wide distribution of views. Some favor the Copenhagen interpretation. Others support many worlds, Bohmian mechanics, or more recent approaches like cubism or relational quantum mechanics. There is no overwhelming consensus. Instead, there is a landscape of perspectives, each with its own strengths and challenges. This diversity is not due to a lack of expertise. It reflects deeper philosophical differences. For example, some physicists place a strong emphasis on realism. They prefer interpretations in which physical systems have definite properties, even if those properties are hidden or not directly observable. This inclination can lead them toward approaches like Bohmian mechanics, or certain forms of hidden variable theories. Others are more comfortable with abandoning strict realism, accepting that properties may not be well defined until interactions occur. This perspective aligns more closely with interpretations like Copenhagen or relational quantum mechanics. There are also differences in how physicists think about probability. Some view probabilities as fundamental features of nature, irreducible and intrinsic. Others see them as expressions of incomplete knowledge, even in a quantum context. These differences are not just technical. They are tied to broader views about what a scientific theory should provide. Should it offer a detailed picture of an underlying reality, even if that picture is complex? Or should it focus on predicting observable outcomes without committing to a specific ontology? Quantum mechanics allows for both approaches, at least to some extent. This flexibility is part of what makes it so powerful, but also part of what makes it so open to interpretation. It is also worth noting that the situation is not static. New ideas continue to emerge. Developments in quantum information theory, experiments testing the foundations of quantum mechanics, and advances in related fields all contribute to ongoing discussions. Some interpretations that were once considered fringe have gained more attention, while others have been refined or reconsidered. Despite this activity, the core mathematical structure remains unchanged. The Schrödinger equation, the rules for calculating probabilities, the framework of Hilbert space, all of these continue to provide a consistent foundation. This leads to an interesting situation, a theory that is both highly successful and not fully settled in its meaning. In many areas of science, disagreement is often seen as a sign that something is incomplete or incorrect. But in this case, the disagreement exists alongside a theory that works exceptionally well. This suggests that the source of the disagreement is not a flaw in the predictions, but a richness in the interpretation. Quantum mechanics may be telling us something about reality that can be understood in multiple, equally valid ways, at least within the limits of current evidence. This is not entirely unprecedented. In other areas of physics, different models can describe the same phenomena from different perspectives. Wave and particle descriptions of light, for example, were once seen as competing views, but are now understood as complementary aspects of a deeper theory. In quantum mechanics, however, the differences between interpretations often touch on more fundamental questions. Questions about what exists, what can be known, and how those two ideas are related. These are questions that extend beyond physics into philosophy, and because they are not always resolved by experiment alone, they leave room for different viewpoints to coexist. There is a certain quiet value in this. It means that the theory is not closed. It continues to invite exploration, not just in terms of new experiments, but in terms of how we think about its meaning. It also reminds us that science is not only about answers, it is also about the frameworks we use to understand those answers, and sometimes a single set of equations can support more than one framework. So when physicists disagree about quantum mechanics, it is not necessarily a sign of confusion or weakness. It is a reflection of the depth of the subject, a recognition that we are dealing with a theory that is both precise and subtle, one that reaches into questions that do not always have a single, definitive answer. And perhaps, in a quiet way, that is part of what makes it so compelling. Not just a set of rules for predicting outcomes, but a window into a deeper conversation about the nature of reality itself. A conversation that is still unfolding, shaped by both calculation and interpretation, and open to new insights as our understanding continues to grow. There is a quiet expectation that often accompanies the idea of scientific progress. That as knowledge increases, mystery will fade. That each discovery will replace uncertainty with clarity, confusion with understanding, and questions with answers that settle comfortably into place. And in many areas, this is exactly what happens. When Isaac Newton described the motion of planets, he replaced centuries of speculation with precise laws. When James Clerk Maxwell unified electricity and magnetism, he revealed a deeper simplicity beneath seemingly separate phenomena. When Charles Darwin explained the mechanism of natural selection, he provided a coherent framework for understanding the diversity of life. In each case, science brought a sense of resolution. It made the world feel more understandable, more predictable, more complete. But not all discoveries follow this pattern. Sometimes, the deeper we look, the more the nature of the questions begins to change. Quantum theory is one of those cases. It does not simply replace older ideas with clearer ones. It reveals that some of the assumptions underlying those older ideas were never as solid as they seemed. The expectation that objects have definite properties at all times. The belief that causes and effects follow a single, unambiguous path. The intuition that space and time provide a stable, continuous background for events. Each of these ideas works well within the domain of everyday experience, but at the quantum level, they become less certain. Not because the theory fails, but because it shows that reality is structured in a way that does not fully align with those expectations. In this sense, quantum mechanics does not remove mystery, it transforms it. The mystery shifts from questions of calculation, which the theory answers with remarkable precision, to questions of interpretation, meaning, and perspective. Why do probabilities play such a central role? What is the nature of superposition? How should we understand entanglement, or the role of measurement? These are not questions that can be resolved by a single experiment or a single equation. They are questions that arise naturally from the structure of the theory itself, and they tend to lead, not to final answers, but to deeper layers of inquiry. This is not unique to quantum mechanics, but it is particularly clear here. In many areas of science, progress does not eliminate mystery entirely. It replaces simpler mysteries with more subtle ones. As understanding grows, the boundaries of what is known expand, and with them, the edges of what is not yet understood. This process can be seen throughout the history of physics. The discovery of atoms did not end inquiry into the nature of matter. It led to questions about subatomic particles. Those questions, in turn, led to quantum mechanics, and quantum mechanics has opened the door to even deeper questions about information, space-time, and the structure of reality itself. Each step forward brings both clarity and new uncertainty. In this light, mystery is not an obstacle. It is a natural outcome of deeper inquiry, a sign that our understanding is reaching into areas where familiar concepts begin to lose their clarity. Quantum theory, in particular, invites a kind of intellectual humility. It reminds us that the universe is not obligated to conform to our intuitions, that the patterns we find comfortable are shaped by our experience, not by any requirement that reality must follow those patterns at all scales. This humility is not a limitation. It is a strength. It allows us to approach new ideas without insisting that they fit into existing frameworks. It encourages openness to perspectives that may initially feel unfamiliar or even counterintuitive. It also creates space for multiple interpretations to coexist. As we have seen, different ways of understanding quantum mechanics can offer different insights, each highlighting certain aspects of the theory, while leaving others less emphasized. This diversity of viewpoints is not a weakness of the field. It reflects the richness of the subject, a recognition that a single simple narrative may not capture all that is going on. There is also something quietly reassuring in this. The presence of mystery does not mean that we are lost. It means that there is still more to explore. The equations remain reliable. The experiments remain consistent. The technology built on quantum principles continues to function with precision. What remains open is the interpretation, the deeper story about what these results mean. And perhaps that openness is part of the value. It keeps the conversation alive. It allows for new ideas to emerge, for old assumptions to be revisited, and for understanding to evolve over time. In a way, quantum mechanics expands our perspective. It does not simplify the world into a more familiar shape. It reveals that the world may be more intricate, more subtle, and more layered than we had previously imagined. And in doing so, it gently shifts our expectations. From seeking complete certainty to appreciating structured uncertainty, from expecting intuitive clarity to accepting that some aspects of reality may remain conceptually challenging, from viewing mystery as a problem to be solved to seeing it as a feature of a deeper and more complex universe. As we move forward, this perspective offers a quiet transition, not toward a final answer that resolves all questions, but toward a broader understanding. One that holds both knowledge and mystery together, one that recognizes that even in a universe described with extraordinary precision, there is still room for wonder. And that perhaps, in that balance, between what we can explain and what we are still learning to understand, there is something essential about the nature of discovery itself.